Hello everyone, this is Danica and I will be doing my bonus video for MHF-4U1 Unit 13. So I will be doing question 8 from page 512. Okay, so the question is, carbon-14 is used by scientists to estimate how long ago a plant or animal lived. The half-life of carbon-14 is 5,730 years. A particular plant contained 100 grams of carbon-14 at the time that it died. Part A. How much carbon-14 would remain after 5,730 years? Okay, so by looking at my question, I can tell that this is I need to use my half-life formula. And I know that my general half-life formula is M of T is equal to A 1/2 to the power of T over H, where A is the initial amount of the substance, times 1/2 to the power of T over H, where T represents time and H represents the half-life. So in my question, I'm given the half-life of the carbon, which is 5,730 years. Okay, and I'm also given, so it says a particular plant contained 100 grams of carbon-14 at the time that it died. So it contained 100 grams at the time that it died. So I'm given the amount, initial amount, at the time that it died, which is 100 grams. Sorry, the mass. So that's the mass that the plant was at when it died. So I'm asked to find, so for part A, I'm asked to find how much carbon-14 would remain after 5,730 years. So I'm asked to find how much carbon-14 would remain. So that's M of T. So I'm solving for M of T, so which is equal to 100. I plug in 100 for A because that's the amount that was remaining at the time it died, 100 grams, times 1/2 to the power of T over, I'm given T, which is 5,730 years, because it's asking me how much was remaining after 5,730 years. So I plug that in for T over 5,730, which is the half-life, and which I'm given in my original question. So when I do this, I can simplify. So 100 times 1/2, and 5,730 over 5,730 is just 1. So this is equal to 50. M of T is equal to 50 grams, because it's asking us how much carbon-14 would remain. So we have to put our answer in grams because it's given to us in grams in the original question. So therefore, 50 grams of carbon-14 would remain after 5,730 years. Okay, so for part B says write an equation to represent the amount of carbon-14 that remains after T years. Okay, so they're just asking us to write a general equation to, we just have to set up an equation for this problem. So M of T, which I've kind of already done in part A. So M of T is equal to, we know A, which is the initial amount, times 1/2 to the power of T over H, where T is time and H is the half-life. So M of T is equal to 100, because 100 is the is our initial, like our A value in this question, because that was how much carbon-14 the plant had when it died, times 1/2 to the power of T over 5,730. And I can plug in 5,730 for H because I'm given the half-life of carbon-14 in the original question. So yeah, so therefore an equation that represents the amount of carbon-14 that remains after T years is M of T is equal to 100, 0.5 to the power of T over 5,730. So this is my equation. Okay, for part B. Now part C asks us, after how many years would 80 grams of carbon-14 remain? So we're asked to find after how many years. So I know that I'm asked to find time. So I am asked to find time, which is represented by t. Okay, so and I'm given the amount of carbon. So I'm given the amount of carbon in my question, in the question. So it says, after how many years would 80 grams of carbon-14 remain, which is m of t. So I plug my values into my equation. 80 is equal to 100, 0.5 to the power of t over 5,730. And now I just simplify. So divided by 100. So I can divide by 100. Simplify. So I get 0.8 and 0.5 to the power of t over 5,730. Okay, so I want to isolate for t, and so in order to isolate for t, I would have to take the log of both sides, like we learned in units 1 to 3. So log 0.8 is equal to log 0.5 to the power of t over 5,730, which is equal to but I know that this, according to the laws of logarithms, this can be used as a double exponent, where I can put t over 5,730 in front of the log. So log 0.8 is equal to t over 5,730 times log 0.5. Okay, so I can now simplify even further by so I can isolate for t by multiplying log 0.8 by 5,730 over 1, and then t 5,730 over 5,730 over 1. So I take the reciprocal of it in order for 5,730 to cancel out. So multiplied by log 0.5. So it cancels out, and so I get negative 555.2943, which is equal to t log 0.5. Okay, but I still have this log 0.5 that I want to get rid of. So I just divide negative 555.2943 divided by log 0.5 to isolate for t. So I do that on both sides. So I'm dividing my log 0.5, cancels out, and this is equal to 1,844.6479, which is equal to t. So there, I've isolated for t, and now I round up my answers. So since it's asked me to, part C is asking me, after how many years would 80 grams of carbon-14 remain? So after how many years? So about 1,844 years. So therefore, after 1,844 years, 80 grams of carbon-14 would remain. Okay, and finally, for part D. Part D is asked me to estimate the instantaneous rate of change at 100 years. So the instantaneous rate of change at 100 years. Okay, so 100 years. So I take two values that are extremely close to 100. So I can take 99.9. So I'm going to choose the preceding and following interval methods. So 99.9 and 100.1. Okay, so I plug these values into t. So since I'm given 100 years is time, so these are values of t. So I plug this into my equation. and I get 98.7988. So okay, and I plug in 100.1, so and I get 7,964. Okay, so just round this up to 2 decimal places, so 98.80. Okay, so 100.1, 98.80 is my, this is my x1 y1 coordinate, and this is my x2 y2 coordinate. Okay, so now I can plug this into the instantaneous rate of change formula. So plug this into the formula. Y squared minus y1 over x squared minus x1, which is equal to 98.80 minus 98.7. So actually, sorry, for this part, I'm not going to round up my answer. I'm just going to leave it at 98.7964. Okay. So now, plug in my values. So 98 so my y2 value, which is 98.7964, minus my y1 value, which is 98.7988, divided by my x2 value, which is 100.1, minus my x1 value, which is 99.9. And then do this, I get negative 0.012. So that means negative 0.012 grams per year, because it's asking us the instantaneous rate of change at 100 years. Oh, sorry. So that would mean at 100 years, the instantaneous rate of change. So at 100 years, the instantaneous rate of change is negative 0.012 grams. Okay, and so just to let you know, for part D, you may get a different answer than the one I got. It may be off by a few decimal places, but that doesn't mean your answer is wrong. It's just as long as it's pretty close to my answer, because it all depends on the values you take for T, because as long as they're values that are close to 100, like really close to 100, you should get an answer that is around negative 0.012 for part D. So just to let you know that whenever, because the instantaneous rate of change is just a best estimate. So yeah, as long as you take two values that are really close to 100, so I wouldn't go off more than 0.10. So yeah, as long as you take two values that are really close to 100, your answer should be around the one that I got. Okay, thank you for listening, and good luck on your test.